Okay, so before we finish up 11.3, there's definitely some concepts we need to review and also teach, technically, with talking about rotational inertia and torque. And what we're going to be looking at is going to be a situation where we have basically a lever. Technically, it's a seesaw with masses on the end. My dog is whining over here. Hopefully, he's not being annoying. Yesterday, he was chewing on a bone, and it was, yeah. Anyways, so we're going to need to review that stuff before we can go on with the 11.3 practice, so we have all of the skills we need in order to actually do those problems. So this is basically a review. We have learned this before, that when you have rotational inertia with mass concentrated in different areas, we need to add it together to get the rotational inertia as a whole. Again, that's so we can do problems like torque net equals the rotational inertia times the acceleration. To get this I, in this situation, for example, we have a merry-go-round with a kid sitting on it. That's different concentrations of masses. We have the mass itself of the merry-go-round and how that's kind of distributed. And then we have the mass of the child and where that's distributed. So to get the I, we need to add both of them together. So we have a merry-go-round here to find our total inertia, with radius 3 meters and mass 100 kilograms is spinning, while a child, mass 20 kilograms, sits 2 meters from the center. This is important, the difference, the radius versus where the kid is sitting, that's going to matter. So we're going to model a merry-go-round as a disk with this rotational inertia, mr squared over 2, where m is the mass of the disk and r is the radius. Now notice they don't tell us a formula for the child. We can assume then that the child is a normal rotational inertia of just like one ball of concentrated mass. That's what we're going to say it is. So what's our normal when they don't tell us rotational inertia formula? It's mr squared. So just mr squared by itself is just like one ball of concentrated mass. Here we have a disk though where the mass is kind of flattened out. So they have a special formula for that. So again, our total inertia is going to be the inertia of the child plus the inertia of the merry-go-round. So we're going to kind of expand this out. The formula, once again, we said for the child was just going to be m. I'm going to use a lot of subscripts here. You technically don't have to. You just have to be very careful to understand which masses and which radiuses go with what. This is the mass of the child. I'm also going to put a C here because this radius refers to the distance from the center of rotation. So notice the kid is sitting 2 meters from the center. That's going to matter. Plus, excuse me, the mass of the merry-go-round. Again, you could just say m and m, but you would have to be very careful to remember that they're different masses, right? This is the mass of the merry-go-round times its r squared. Now again, this r refers to the radius itself. So these are going to be different r's, which is why I'm putting different subscripts on them. Divide by 2. So there it is. We just got to plug everything in. It's very simple when we're just looking at one thing. The hard part is when you're doing a question where something like this, net torque. You have to find the I, and then you have to go and find the net torque separately, and then you got to do some other stuff. It can get complicated. That's why we're trying to break it down into the small skills right now. Okay, so the mass of the child is 20. I'm going to go ahead and drop this down, actually. 20. R is the distance from center, which would be 2. Again, if that child sat farther out on the merry-go-round, it would be more difficult. It would take more force, more power, more energy, all of that, to get him to go around. Because he's sitting closer to center, it's not as difficult. Remember that if he was sitting at center, he would have no inertia. He'd just be sitting there rotating. It would be super easy for him to rotate. Again, you've experienced this if you've ever gone on one of those rides where they fling you up against the walls. The further out you are, the more force you feel. And the mass of the merry-go-round now we have is 100. The radius is 3 now. Once again, the difference is in the r's and what they mean. This is the distance from center. This is the actual radius. Divide by 2. And then we just got to plug this all in. We got 20 times 4 plus. We should get 530. Once again, I know inertia has kind of weird units. Remember that since it's mass and radius squared, typically, mass is kilograms, radius squared is meter squared. So this is kilograms, meter squared. And there we go. That's the rotational inertia that we could then use in a net torque equation when doing Newton's second law there. So this one's a little bit different now. This is something not technically new. It's just a weird formula we need to talk about. So two children sit on the ends of a teeter-totter, seesaw, of mass 75 kilograms. The teeter-totter itself is 75 kilograms. One child is 20, the other is 15. The teeter-totter is made so that even though its length, grammar, its length is 4 meters, the fulcrum, let's talk about this real quick. And what we're going to do after this is more fulcrum questions. What the fulcrum is it's the balancing point. So if you're on a teeter-totter, wherever they put the balancing point, so it is at a point 1.5 meters from the child who has a mass 20 kilograms. So the children are here on the ends. There's 20 kilograms. There's 15 kilograms. So we're just going to pretend they are on the exact ends, yeah? So they are exactly the same distance from center. Now again, even though this is 4 meters all the way around, the fulcrum point, which again is the balance point, is only 1.5 meters in. So the important thing to notice here is that it's not located at the center of mass of this. So what ends up happening here, this is a little bit weird. When we do the inertia of this, what ends up happening is we have 3 inertias going on here. We have child 1, I'm going to call him. We have the inertia of child 2. And then what we also have is the inertia of the center of mass of the stick. The center of mass is located right here, right, at a distance of, we can put 2 there because it's gonna be the dead center, so it's 2 from either side, right? Sorry, however you want to label that. So the center of mass of the stick causes it to tilt. This is why, which we're going to look at actually later. If I just have a stick and it's not balancing at the center of mass, this is why it tilts, right? That center of mass actually exerts a torque, and that's why it starts to rotate. So this is not something we've talked about yet. So that's why we needed to go in this. So we have 3 inertias here. Again, we're going to have all of these. The inertia from the center of mass, that's what CM is this formula. Use the formula talking about the stick. That's going to be, again, for the center of mass. So we got to plug these in. Once again, they don't tell us the formulas for the children, so we just assume they are just like straight balls of mass. That's the formula we're going to use. So take a moment. With this formula in for the center of mass, go ahead and write this out with the inertia formulas for the 2 children as well. Okay, so again, I'm going to use subscripts. If you don't, you just have to be very careful not to mix things up. We have mass of child 1 times its radius. Now, something to clarify again, this R still stands for the distance from the fulcrum point. This radius is always the distance from the rotating point. And in this case, this is the rotating point. When we're talking about how these masses interact, right? We are referring to the distance from the fulcrum point. So just keep that in mind for later. Now I have the mass of child 2 times its distance, once again, which is why I'm putting subscripts. Notice the mass of the second child has a different distance to the fulcrum, to the rotation point, than mass 1. Be very careful with that. And then we have this formula. So we have the mass of the teeter-totter. I'm just going to put T. L, we know what L is referring to, the length of it, over 12, plus the mass of the teeter-totter. D is the distance from the center of mass to the fulcrum point. So once again, we could even put this as R, meaning in the same sense, these R's, all of these R's and this D referred to the distance to the fulcrum point. Since we're referring to right here, this is the center of mass, the inertia of that, yeah. That's what this D refers to, the distance from the center of mass to the fulcrum point. So what I want you to do is try it. I'm going to move my picture here so it's not covered up. Once again, the R's and the D refers to those things' distance to here, to the fulcrum point. We have these two masses on the end, and we have the center of mass here being at 2. I hope that makes sense. If this is 4, I kind of skipped there quickly. If this is 4, the center of mass is at 2 just because this is an even stick. Center of mass is dead center. Try and plug it in and we can come back and check. Okay, so let's see what we got. So the mass of child 1 is 20. Its distance to the fulcrum point is 1.5 you should have used. Again, that R is referring to the distance, major, to the center of rotation. And this is the center of rotation while this is the center of mass. Different things, yes? So there's our first child, plus our second child has a mass of 15 kilograms times its distance to the center of rotation. Well, if this is 1.5 here and I have 4, this is going to be a distance here of 2.5. So that's what we should have used for child 2. Again, these R's refer to the distance to the center of rotation. Plus, now we have the inertia for the center of mass. So again, we have the mass of the teeter-totter, which is 75 kilograms, times its length, which is 4, divided by 12. Plus, being careful here that once again, the mass is 75. The distance here is the distance, lots of labels on this picture, from the center of mass, that's not centimeters, that's center of mass, to the fulcrum point. What is that distance again? You should have used 0.5. 1.5 to 2, that's a distance of 0.5. So again, technically not hard. Technically, I hope it makes sense where these numbers come from. You just really have to keep them straight, go slow, and double check. Okay, so it's just a matter of plugging everything in now. So 20 times 1.5 squared plus 15 times 2.5 squared plus 75 times 4 squared divided by 12 plus 75 times 0.5 squared. Oops. Okay, if I plugged everything in right, hopefully I did. We got a rotational inertia of 257.5. Once again, this is kilograms meters squared. Okay, and that is our answer. So again, we're gonna have to combine this together, unfortunately, with other things. We would use, in the homework we're gonna be doing, in the practice we're gonna be doing, or we'll start in class, we're going to use this in, again, the net torque for Newton's second law, to find how this is tilting, how the acceleration of this is going. So a couple more questions here that we're gonna have to, again, just they're little pieces of skills that we need to do a bigger problem, right? So we're gonna have some questions about fulcrum points. So what we just talked about here is that the fulcrum, the center of mass exerts a torque on our object when the fulcrum point is not at the center of mass. If the fulcrum point is at the center of mass, no torque is exerted, right? Again, if we're pushing on that center of mass, nothing happens, yeah? So here though, we have a bar of 5 kilograms and length 5 meters, rests on a fulcrum point, a distance of 4 meters in. So I'm gonna draw my picture here. We always need to draw our pictures, gonna be very careful. This is 5 meters. My fulcrum point is here, a distance of 4 meters. So to start with, what's going to end up happening is, again, this is just a normal bar. where is the center of mass? This is 5 meters long. Where is our center of mass located? At 2.5 meters in. This is located 4 meters in, but the center is at 2.5. So what's going to happen here is there is going to be a torque exerted by the center of mass. Yeah. And that's what this question is asking. What is the torque acting on the bar? Now, I need to rephrase this actually real quick. By the center of mass. There we go. And in which direction is the torque acting? So here's my center of mass. So keep in mind that that is, you can picture which way our bar is going to tilt. It's going to tilt to the left, right? It's going to tilt down this direction because our center of mass is located to the left of the fulcrum point, right? So we can imagine our bar is tilting down to the left. So once again, what is our formula for torque? We have R times F, yeah? Now in this case, our R is once again the distance to the center of rotation. Torque is always referring to that, the distance to the center of rotation. So think a moment. Our rotation is occurring right here on the fulcrum point. We're talking about the center of mass. What is the distance from the center of rotation, the fulcrum point, to our center of mass? Well, if we have a distance of 4 meters and it's 2.5 up to this point, that means we would just subtract it. That's a distance of 1.5 meters right there from our center of mass to the fulcrum point. So that's going to be our radius, 1.5. Now our force is actually the force of gravity of the bar. That center of mass, we can pretend, again, the whole definition of center of mass is we can do all of our math like all of the mass is concentrated in that point. That's the definition of center of mass, right? That's why if I place my finger right there on the bar, it would balance. We can pretend all of the mass is concentrated there. So what is going to be the force of gravity of the bar then? The bar is 5 kilograms, so 5 times 10, that's going to be the force of gravity pulling down right there. Again, that's the center of mass. We can pretend, we can do the math, and it works out that all of the mass is centered, concentrated right there. So this is it. This is our torque. This is, again, the distance from the center rotation point times 5 times 10. Let's see, it should be 75, right? 75. And again, this is a Newton meter. It's been a while since I've written those units down. Newtons for force, meters for radius. They call it a Newton meter. And there we go. That's the torque. Now I want you to make a note of which direction the torque is acting. Notice it's pulling down. Now I'm not saying the direction of the torque vector. I know this is confusing, but because we talked about that yesterday with the right hand rule, they would say the direction of the torque vector if that were the case. But it's pulling down this way. Think about if this thing kept spinning in that direction. Obviously, it's going to go and then stop. But if it kept spinning in that direction, is that clockwise or counterclockwise? That is counterclockwise, pulling down this way. If I were to follow that into a circle, this is counterclockwise. So they write that as CCW, counterclockwise. So again, typically we call that a positive direction because if you notice coming around this way, it starts us to go to the right. Yeah, that would be a positive direction. We could call it negative if we wanted to. Again, the math would work out. Now let's do this question. What if the fulcrum point was at 1 meter? Now I meant to, no, this is right, 1 meter in. So let's draw our picture now. So we have, again, 5 meters total. The fulcrum point is now here at 1 meter in. What we need to realize is where is our center of mass again? There's no masses on the bar, but that center of mass is going to cause a torque. So once again, label the center of mass, and then we're going to find the torque of it. I want you to try this. You're going to notice something for a reason. Label on your picture the center of mass. Find the, sorry. You guys good? Havoc. You okay? Come on. Wait. I can be okay? Okay. Oh my gosh, Chris. I gotta cut this out of the video now. Okay, anyways, sorry, my dog was just roughhousing. Okay, so once again, label the center of mass, where it's at, and then go from there. Okay, center of mass is here. This is a distance of 2.5 meters in, however you need to label it. Boys, hey, shush. Calm down. There's our center of mass pulling down. And again, all of the weight of the bar is pulling down right there. So what did we say for R? What's our distance from the center of mass to the center of rotation, to the fulcrum point? Still 1.5. It's actually still 1.5 here, but we're going to notice something a little bit different. That radius is still 1.5. The force is still the mass of the bar times gravity. So it is still going to be 75 Newton meters, but let's look at this now. What's our direction now? My center of mass is now to the right of my fulcrum point. So once again, if we follow this around with our finger, as if it were to keep turning, which direction is that now? That's clockwise. Now the direction has changed. So again, we need to be careful about the direction of the center of mass. Depending on which side of the fulcrum point the center of mass is on, that will change which way it tilts. Again, that should make sense. Obviously, we can understand that this would start tilting to the right now, yeah? In that case, this would be a clockwise rotation. Again, hopefully you understand this is clockwise. It follows the numbers of a clock, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 goes in that direction. So we just need to be careful as well again and note which side of the fulcrum point the center of mass is on. Okay, we're going to do one more little piece here that again, we're going to have to put together all of these pieces in one question that we're going to work through in class. So the difference here is that we are pulling out the mass of the bar now. When it says negligible mass, that means the bar exerts no torque or can't exert any torque. Yeah, obviously, again, if it was balanced at the center anyways, it would exert no torque. But since it says negligible mass, we ignore it. So we have two masses placed on this bar, and one mass is placed at the 1 meter mark, and one mass is placed at the 3.75. So let's draw our picture to try and find the net torque. So here is a 4 meter bar. We have the 15 kilogram is placed at the 1 meter mark. That's 4. Oops, that's my arrow. So this is 15 kilograms. This is the 1 meter mark. And then we have 10 kilograms. Placed at the 3.75 meter mark. Now, you can label it this way. However, what's important to note really is the distance from the fulcrum point. So our fulcrum is placed at the midpoint of the bar. So I'm going to redraw this picture, focusing on, now that I know that this is 1 meter in and 3.75 meters in, now I'm focusing on the distances from the midpoint. So let's try this again. Focusing on the distance from the fulcrum, which is at the midpoint. So let's draw this. I'm going to put my fulcrum on here, which is at 2 meters in. Shoot, I wanted you to figure that out. I can put a question in. You're good. If it's 4 meters total, that's 2 meters in, right? So I want you to, again, we have the 15 kilogram and we have the 10 kilogram. I want you to label these two distances here. Take a moment to do that. The midpoint is 2 meters in, and we know where the 15 kilogram was placed and where the 10 kilogram was placed. Go ahead and label these distances. Okay, well, if we are 1 meter in here, this is another 1 meter to get to 2 meters. And to get from 2 to 3.75, that's 1.75. So those are our distances from the center of rotation. Once again, it just so happens that our fulcrum, that our center of rotation, is the center of mass because the midpoint of the bar. But we just need to be careful that we are understanding I am measuring this distance specifically to the fulcrum. If this fulcrum were placed somewhere else, I would measure to that point. So our torque is going to be two different things. We have this mass pulling on this side. So I'm going to go ahead and say mass 1 plus the torque of mass 2. Let me rephrase that. I'm going to edit this video so much. Oh my gosh. Torque of mass 1 plus torque of mass 2. Now, what we need to be careful about here is these are pulling in different directions. This is the hard part about torque and rotation, is that they're both pulling down, right? So if we're thinking linearly, both of them pulling down, you'd be like, oh, they're pulling in the same direction. But we know this to not be true. If I'm pulling down over here, that would mean I'm pulling towards the left, right? Correct. If I'm pulling down over here, I'm pulling down towards the right. These are different clockwise and counterclockwise rotations. So we need to call one of them positive and one of them negative. I know it's so weird. These are actually pulling in different directions. And once again, that should make sense. If they were pulling in the same direction, that would mean they are pulling the same side down, but they're not. They're pulling in opposite directions. So let's go ahead and call this one a negative force. It doesn't necessarily matter, again, but we can go ahead and call this one a negative force since this one is listed first. It'll work out either way. Okay, so what we need again is the torque formulas. Take a moment to write the torque formulas here. We have radius of mass 1 times its force plus the radius of mass 2 times its force. I want you to go ahead and plug in. Remember that the force is the force of gravity for those masses. The radius is the distance to the fulcrum. And then be careful, we are calling the mass of 10 to have a negative force because it is pulling in a different direction of rotation than the other. Go ahead and plug it in. Okay, so we have 15 kilograms times its distance is, oops. Okay, so we have a distance of 1 and then a force of 15 times 10. Once again, that's 15 for gravity, right? 10 meters per second squared. Minus, yeah, or I can call the force negative, however you want to say it. The radius for the second mass is 1.75 times its force is 10 times 10. Again, we could call the force negative or we could just put this negative out in front. So we have 1 times 15 times 10, didn't necessarily do that, minus 1.75 times 100. Okay, so we get a net torque of negative 25 Newton meters. Now, what we need to realize here, we called this direction the negative direction. If I have a negative net torque, that means I'm headed in the negative direction. So what is the direction of the rotation? It's going to be clockwise or counterclockwise. Once again, if this is the negative direction, Follow that with your finger around into a circle. Is that clockwise or counterclockwise? That's clockwise, going down and then over. That follows the direction of a clock. So this is the direction of our rotation. Again, if we decided to call this negative, we would have ended up with a positive as our answer, but it would still end up being a clockwise direction because, well, now we called this side positive, which is still clockwise. That's why you get to choose your negative direction. It still works out for what we consider to be clockwise or counterclockwise. Okay, so once again, in class, we're going to put all of this together. All of these concepts, talking about adding together all these different rotational inertias, dealing with the torque of the center of mass, dealing with the torque of these masses, get put together, and we have to try and keep it all straight.